This is the introduction to Chapter 8 in the book, in Lecture Notes 8. I believe it's Chapter 8 in my version of the book. This is nonlinear regression functions. Okay, so we have two graphs here that you can see. One, they're both graphs of two variables, x and y. And the first is a scatter plot, which looks like the relationship is somewhat linear. So we can see kind of what we mean by linear here. Linear is going to be some relationship that is just a line. So if we put our line here, best fit, suppose we estimated a regression model on this data, the best fit would look something like that. So that would be our estimate of y hat equals beta hat 0 plus beta hat 1 x. But what do we do if the data looks like the bottom graph? So the data has some curvature to it. Okay, if we estimate our regression line on this data, it would look something probably like, maybe like this. So if we estimate a linear model on this data, it would look something like this. Maybe beta 1 would look a little better. Better than that even. Might look something like that. The problem here is that we're over predicting at the ends of the line. So we're over predicting over here and over here, but we're under predicting in the middle. So this line is probably not the best fit line for this data. So how do we adjust our regression to capture the curvature here? Well, we're going to use nonlinear regression functions. So maybe we estimate a line that looks something more like, let's use blue or red. So maybe if we had a quadratic term in this model, maybe our regression line would do something like this. So this might be y hat equals beta hat 0 plus beta hat 1 x plus beta hat 2 x squared. So now we're adding a quadratic term to the model. That might be a better fit. So that's what this chapter is about, nonlinear regression functions. So why might we want a nonlinear regression function? If the relationship between x and y is nonlinear, then the effect of x on y depends on the level of x. So just like we had in our chapter 7, our interactions, we said maybe the effect of x depends on z or vice versa. The effect of z depends on x. And in our example, we had the effect of education on wages, that the effect of education on wages depended on the level of experience that a person had, and also depended on a person's gender. So we were interacting experience with education, or interacting gender with education. In this case, we're going to interact the variable with itself. We're going to interact x with itself, or we're going to transform x in some way, or y in some way, that allows this model to have some curvature to it. So when we interact experience with education, we just multiplied experience by education. And likewise, when we interacted gender with education, we were interacting those variables. We were multiplying them together. In this case, we're going to interact x with x. So that's what x squared is here. We're just interacting x with x itself. So why is this important? Well, we know it's important because we can see on this graph here that we're over-predicting and under-predicting in some places. So the simple linear OLS model assumes or imposes the effect of x on y is constant across all x values. If it's constant across all x values, then we get this linear function here, and the slope is constant across x. And that means that the level the effect of a change in x is the same regardless of our level of x, but clearly that's not the case with the data, so we have to allow our model to be flexible enough to allow the effect of x to change depending on the level of x. The problem is that OLS is then misspecified, and that of course leads to a biased estimate of our beta 1 coefficient. So let's look where does this show up in the error terms? Well, just like when we left out important control variables, those variables are contained in the error terms. So let's look at two examples here. Test scores on student-teacher ratios by itself, so that's going to be equation 1. So equation 1 here is just test scores regressed on student-teacher ratios by itself with an error term in red, U1. Equation 2 is going to be test scores regressed on student-teacher ratios and percent English language learners in the class with an error term U2 in green. And we know that U1 then contains percent EL, or the percent of English language learners in the classroom. So U1 is actually just, in our previous example, U1 is this whole thing here. It's going to be beta 2 times percent English learners plus U2 in green. So that's what we have down here. So percent EL is an omitted variable in equation 1 that's contained in the error term, and we knew that it was correlated with student-teacher ratios, and it was a predictor of test scores, so it was going to cause biased estimates of beta 1 in equation 1. What about if student-teacher ratios has some curvature in its relationship to test scores? So maybe in the graph above here, x is student-teacher ratios, and so maybe we'll have x as student-teacher ratios and y equals test scores. So what if the true relationship is actually curved like this? So maybe we need x squared, or student-teacher ratios squared, in the model. So let's look at another example, model 3. We know that percent EL is an important variable, but here we're going to add student-teacher ratio squared to the model. So this is the same as adding student-teacher ratio times student-teacher ratio, or an interaction of student-teacher ratios with itself. Now we have the third error term, U3. So now let's look at what this does to the previous error terms. So now if student-teacher ratio squared is an important variable, U1 is now transformed into what we have down here. U1 is equal to beta 2 plus percent EL plus beta 3 times student-teacher ratio squared plus U3. So it contains not only percent EL, but it also contains student-teacher ratio squared. And then likewise, U2, the green error term, contains the omitted variable student-teacher ratio squared plus U3. So student-teacher ratio squared is an important omitted variable in equations 1 and 2 if the relationship is truly curved, like the graph above. And if student-teacher ratio squared is correlated with student-teacher ratios, which it obviously is, it's the square of it, and it's also an important predictor of test scores, then it's an omitted variable that could cause bias in our estimates of beta 1 in either equation 1 or 2. So takeaways, x2 or x squared or x cubed could be omitted variables that are contained in the error terms that could lead to biased coefficient estimates. Could be x cubed, could be x to the fourth. So the most general nonlinear regression function is written as yi equals some function f of x1i, x2i, all the way up to xki plus ui. So that function f could be anything from squared terms to cubic terms to any sort of polynomial of x1 or x2. We could have interactions of x1 and x2, xk, etc. The assumptions for these nonlinear models are basically the same as before. Assumption number 1, the expected value of the ui conditional on all the x's is equal to 0, which implies that f is the conditional expectation function of y given the x's. The xi's are IID again, outliers are rare, and there's no perfect multicollinearity. So if you have questions about those assumptions, go back to lecture notes 6, I want to say, where we detail those in more, we go over those in more detail. Okay, an example of a nonlinear function of a single independent variable. Polynomials in x. So we could write down the most basic polynomial in x function, so we only have one regressor, x1 or xi in this case. We have yi as a function of xi, yi as a function of xi plus xi squared plus any amount of polynomial terms in x plus all the way up to xi to the k power plus a linear error term. So again, note this is identical to the interaction models from lecture note 7, but now we are interacting x with itself. So this is xi times xi, and here we have xi times xi times xi all the way out to xi k times. So let's do an example in practice. Test scores and district level income in thousands of dollars. All right, the quadratic population specification would be here. Test scores equal to beta 0 plus beta 1 income plus beta 2 income squared. The cubic specification would just be test scores plus equals beta 0 plus beta 1 income plus beta 2 income squared plus beta 3 income cubed. The sample output for the quadratic specification is here, 607.3 plus 3.85 times income minus 0.0423 times income squared. We can use this to predict test scores. So we can take maybe income equal, here's a chart of predicted values, predicted test scores at different levels of income. So this is going to help us understand why it's important to have the income squared in here. So we'll use income equals 10, income equals 20, income equals 30, etc. We'll plug those values into the sample output up here. So I'll put a star here to indicate that I'm talking about the sample output. Okay, so we're plugging in 10 into this equation, the sample output with a star. So if we plug in 10 for income and income squared, that'd be 10 here under income and 100 under income squared. Then what we get out is predicted test score of 641.57. If we plug in 20 for income and then of course 400 for income squared, then the predicted test scores would be 667.38. We take the change in test score here, so the triangle is the change in test scores. So we're going to subtract test scores, the predicted test scores at income equals 20. We'll actually subtract the predicted test scores at income equals 10 from the predicted test scores at income equals 20, and we get 25.81. Then we keep going down and we plug in 30 into the sample output. We get a predicted test score of 684.73. The change in test scores is 17.35. We keep going down this chart here, and we get predicted test scores at different levels of income, and then the change in test scores. So now the important thing here is how the change in test scores is evolving over income levels. So at smaller levels of income, we have larger changes in test scores. 25 is larger than 17, 17 is larger than 8.89, which is then larger than 50, and then eventually we get negative changes in test scores. So what is this implying? It says that the A change in income at lower income levels has a larger effect on test scores than a change in income at higher income levels. And even at around 50, the change in income really doesn't have much of an effect on test scores. So we're plotting out a relationship that looks something like, if we have income here and test scores on the y-axis, we're getting some relationship that looks like this. So that the effect of income, a change in income on test scores at low levels of income is really large. We have a steep slope, but then right around 50, that slope levels off and there's no real effect of a change in income on test scores. Notice at around 60, though, that change in income has a negative effect. Now, this might not be true, that getting even richer has a negative effect on income, but this is what the model predicts. So this could indicate that maybe we need a cubic relationship in the data so that our plot would go something like this if we had a cubic. But we'll look at that a little bit later. So here's another way of thinking about it. So we have test scores and income, the same graph as we had above. If the data really looks like these scatter plots, the scatter plot here with some curvature, then the linear function would fit the blue line without the quadratic term of income in it, but the quadratic regression fits the red line, just like I drew up to the right. So here in this graph, this is actually the same thing as I just drew. That might be about 50, and then going out to $60,000 of per capita income, the effect on test scores is predicted to be negative, which might not be true. So how do we get these predicted values? Let's do one more example. Let's get the predicted change in test scores for a change in income from $5,000 per capita to $6,000 per capita. So what am I doing here? I'm just plugging in this, I'm plugging in 5,000 and 6,000 into my sample regression function, this function up here. So this bit is the sample regression function with $5,000 plugged in, or 5 because income is in thousands of dollars. So we'll put 5 there. And this bit is the sample regression function with 6,000 plugged in, or $6,000. So then we just plug in those values. The intercept's always going to cancel out. Calculate it, and we get 3.4. So this implies that going from $5,000 to $6,000 per capita in income causes a 3.4 unit improvement in test scores for that $1,000 income increase. Now, this is not going to be the same as if we went from $10,000 to $11,000, or we went from $25,000 to $26,000, and that's the point of this. The point is that the effect of income on test scores depends on the level of income. The effect of income on test scores is not the same at low levels of income as it is for high levels of income. So here's a do-it-yourself at home problem. What is the effect of a change from $65,000 to $66,000 per capita? So you're going to take this equation, this one that I'm starring here, and just plug in 65 and 66 and see what you get. So pause the video and see what you get. If you got something negative, then you got the right answer. Now the point here is that we're going to be somewhere out 65 right around here. So the slope of this curve is going to be negative, indicating that an additional $1,000 of per capita income around $65,000 has a negative effect on test scores. Now you have to ask yourself the question, do you believe this? Do you think the data in practice keeps going down like that, or does the data kind of level off? And if so, are we under-predicting the effect at higher levels of income? And how can we fix it?